Hello, everyone, and welcome. My name is Juan Scott. I'm the Executive Director of the 3MEF Consortium, and today we're hosting this webinar with Additive Flow, talking about their software and the manufacturing process optimization with Zeiss and National Physics Laboratory. Additive Flow is a member of the 3MEF Consortium, and what I'm most excited about their software connectivity via 3MEF is they have the most advanced communication of what's happening within a part of any software that I'm aware of. And for that, they're using the volumetric file extension of the 3MEF format. But I'll let Alexander and his team, along with Curtis Frederick, Peter Williams, and Tony Fry, talk about the process here in this webinar. And I'll just be here to host to answer any questions. So if you have any questions, please put them in the Q&A. Do not use the chat. We won't be answering those questions, and we'll present them to the team at the end of the call. And so now, Alexander, take it away.
Pleasure. Thank you, Duan, for the invitation, and also to 3MEF Consortium, not just for the work that's been done to date, but also all of the kind of vision pushing to make AM real. So today we're here, we're Additive Flow. I'm the CEO of Additive Flow, Alexander Pluk, and we've got three people speaking, including myself today. So Additive Flow software that optimizes the production process within additive manufacturing. Really excited here to have Curtis and Tony. Been working with each of them now for more than a year. Curtis since 2019 and Tony since really the end of 2019. And our software is, I think, really special in being able to give this validated prediction of how the production process can both cost less and also achieve those engineering goals. I've got a background in manufacturing engineering, in materials. Curtis, please do introduce yourself.
Hi there. I'm Curtis Frederick. I'm the additive manufacturing application scientist for Zeiss. And I have backgrounds in process parameter development, and with Zeiss I've been working a lot with X-ray CT and combining X-ray CT with process parameter development.
Go ahead, Tony.
Hi, I'm Tony Fry, Principal Research Scientist here at the National Physical Laboratory in the UK, focusing on techniques, procedures and processes for assured measurement data to support additive manufacturing.
Thanks, guys. So we'll be hearing from each of them in a moment, but why are we doing this webinar? Why are we talking about this now? Well, Additive Flow's got a long history. We've been working on the validation of our technology now for over 4 years, and we're really careful about what metrics we put out into the market so we can really have this validated technology. And I think we're standing at this threshold now where with new technologies such as ours that can optimize production, also the developments in materials and hardware, it is now becoming viable to address industrial applications within AM, and that's really what our software is here to fix. And it's to really make your lives easier as engineers. So, lack of process knowledge, I would say, is one of the key blockers to AM really lifting off. There's lots of manual, tacit knowledge workflows in place within those established within AM, and for good reason too. Lives are at stake. These components are doing a real job in the world. AM is complex. There's hundreds of variables that can determine success or failure. They're sensitive variables. Any small change in those variables can break production. And that's not good for anyone. But what ends up happening is we end up maybe over-engineering some aspects of it. Costs are quite high. And very often that journey from potential application to validated business case, validated process can seem quite long. It can seem quite hard to achieve. And even after getting through that, we can still result in failure. And Additive Flow and myself, we've seen that personally. Tony's seen that, Curtis has seen that, and I'm sure everyone within AM have kind of been on that journey. So our software is here to help solve that. So working with people like Zeiss, we've reduced quality assurance costs by 75%. With NPL, we've got a workflow here that will be demonstrated here. So we did this process qualification for our technology and kind of applying it to a new material and machine in 3 months. So that's generally, say, 4 times faster than the average time that it takes to develop a new process. And even more than that, we could take those models and scale them. And so let's talk about how that works. So our technology here, effectively, we are able to simulate and optimize not just that production process, so the way the laser is interacting, say, with laser-powered bed fusion, with the material in the bed, but also those end part requirements, and mediate volumetrically where different parameters should be placed within those build parameter decisions, predicting how those parts are going to perform, and also mitigating things like cracking. So, for example, we've been able to improve the production speed by 50 to 300%, leveraging in-process and post-process data for zero non-conformance components at the end. We've reduced cracking from things like 44 down to 0 with applications with high-strength tool steels. And crucially, it doesn't take a long time to do our computation. We've got a bunch of AI modules as well as traditional and quite advanced classical algorithms that are up to more than 2,000 times faster computing. So, generally an optimization cycle with our technology could take anywhere from a few minutes up to about 10 minutes. And that's equivalent to about the same computation time that maybe a month or more could be done. And we're strongly focused on sustainability as well and reducing energy use. So we've got some really strong results there. And you can see in the center here our software workflow working and trading off. But I won't be talking about it. We'll have our great speakers speaking with us today. And just kind of call out to 3MF. So what Juan mentioned is we've really introduced 3MF from the beginning into our workflow, specifically with Autodesk and the Netfabb product, which is really advanced on generating those toolpaths. So once we've got our optimized volumetric parameter sets, as we can see here, and we've decided we want to have a particular cost reduction or a particular component we want to make, with one file exchange that can be loaded up within Netfabb, and you can see these toolpaths directly happening. And so that's a workflow that can take about 10 minutes. And really, it's only two simple steps, an export and an import, to get that in play. And it saves us from messing around with mesh interfaces and so on. So we'll be doing another study on that later, another webinar on that later. Hopefully, Juan can bring us in with some of our friends at Autodesk to make that happen. But today, I'm going to hand over now to NPL and then to Zeiss, to talk about how did this qualification process happen. And there's really 3 key steps that we've used to do this. We've built a relationship using different data, we've optimized, and then we validated that optimization. And what's really great here is NPL and Zeiss have done that same workflow, just use different data at different steps. So happy, Tony, to take over?
Yeah, perfect. So what I want to talk through is the workflow process that we followed and we developed alongside Additive Flow. So really, it was all about generating the data and then passing it through the Additive Flow software to generate the optimized solution at the end and then validate that. So to start that process off, what we did was using the grid array sample you see in the top left-hand corner of the slide here. We were able to print or have printed a number of different processing conditions within that sample. We actually used 3 of these, so there was 49 different processing conditions per block. They're about 25 millimeters by 25 millimeters square. We then used a combination of optical microscopy, scanning indentation, microhardness measurements, and after that, impact excitation to look at what the actual properties of the material is. You can see in the plot there, oh, too fast, back one. You can see in the plot there that within that range of processing conditions, there were situations where we had quite high levels of lack of fusion, so we had high porosity, and along the other axis where there was too much energy going into the actual build process, the material was boiling, and we kind of had these huge bubbles appearing, and again large amounts of porosity in the actual material itself. But within that center section, we kind of hit a sweet spot where we had quite well consolidated material. We didn't have instances of boiling off of material. And so from within that range, we actually down selected 7 processing conditions where we thought that the material was of a high enough quality to be usable, but it also gave a range of print speeds that could be employed within the optimization routine. Let me go on to the next slide now. So what we did, once we selected those 7 processing conditions, we went through the process of building some impact excitation bars. So these are about 100 millimeter long bars. From those bars, we were able to measure using resonance methods the axial elastic modulus, transverse elastic modulus, and the shear modulus of the material. And we could see how that varied as a function of those processing conditions. And we could also measure using impact excitation the density, and again look at how the porosity and the density of the material varied. Once we've done that, we had some miniature tensile test pieces made. You can see in the top image on the slide there. And using non-contact strain measurement, we conducted a number of standard tensile tests. You can see the comparison of the stress strain plots in the graph at the bottom, where the different lines represent the different processing conditions from those 7 that were chosen. So taking all that data, move on to the next slide, we were able to present that to Additive Flow. They were able to use that within their optimization software to generate a final test component. So the final component we chose to use was a standard dog bone tensile test piece with a through hole in the middle of it to act as a stress concentrator. So we knew where we could focus the digital image correlation measurement to see how the stresses and strains varied as a function of the processing conditions used. So there was 3 samples made. There was a fully dense sample. There was a fast sample, which we knew would have a high degree of porosity. And there was the optimized sample. The optimized sample being printed about 60% faster than the standard sample. So if we can go on to the next slide. What you see in the videos here is some digital image correlation videos of those 3 samples. So the one on the left is the porous one. The one in the middle was the fully dense, and the one on the right is the optimized sample. So from those images there, you can see we're kind of getting similar levels of strain around the hole. It's not overly clear in these images, but there is more variation along the test piece length in sample B compared to sample A. And again, in sample C, we also see a little bit of this variation in strain along the sample length. What was really important was when we came to look at what the actual analytical data, the stress strain data was showing us, which we see in this plot here. So the blue curve is the fully dense printed material. The kind of orange brownie curve at the bottom there is the fast print, so the one that we knew was going to have a degree of porosity in there. And the gray line is the optimized sample. So it was fully dense where we needed the strength, but printed faster with a little bit more porosity where we didn't need that strength in the component. So you can see the optimized sample has a slightly lower Young's modulus, so it's not quite as stiff, but in terms of its strength, its UTS and yield, it's very similar to the fully dense material, but printed 60% faster. We go on to the next slide. So just to wrap all that up, that was the kind of process that we went through. We've developed this kind of rapid screening methodology with the inch square samples with the different regions on. Looked at mapping that optically and with indentation techniques. Then generated the stress strain data, which could be used in the optimization software using small scale test pieces. So again, we're minimizing the amount of material we're having to use. We're minimizing the print time. And then using the optimized production parameters, we were able to generate a test artifact and to show that through these mechanical tests, we were getting equivalent mechanical properties, but with a much faster production route. So yeah, quite successful, I think. And back to Alexander.
No, thank you, Tony, for such a clear and crisp walkthrough of that project as well. And we can have Q&A later, but that was really good summation. Also, just for interest, I've also got some of those high impact excitation bars here, so they're not that large. So now we're over to Zeiss. So we'll have the same story. We'll go through how the relationship first was built, what was happening in the optimization, and then the validation. Over to you, Curtis.
Thanks, Alexander. It's great that I get to follow Tony, because I can see how this additive flow software has changed over the years, and how everyone wants to use it in a different way, but we're all trying to do the same thing. We're trying to speed up the additive process. We're trying to validate how we come up with our models. And it's very interesting. The part we have here is our final optimized heat exchanger, and it's part of a series. So the process we came up with needed to be a repeatable process. We needed to speed up and reduce the final cost of the part. We wanted to move it to a production level. So we wanted to move to a larger printer. We need to come up with new process parameters for that. And we wanted to maintain or improve our performance. And we were able to do that by reducing some of the volume that's not needed and optimizing where parameters go. You can go ahead and move on to the next slide. So here we kind of have that stages we went through. The original STLs on the far left. It doesn't have optimized regions, and it's got extra material. Or then we move to the next stage. We've got that removed volume. We've left some areas there for mounting and machining. And then we've got these stages where it's been allocated to regions that need to be faster, that aren't important. And then our final STL comparison to printed part that's been CT scanned. So we know that it worked out in the end. To create your process parameters and scale up your machine or your process to production scale, you need to use process parameters that increase the build rate. We were moving to an SLM 500, so we had a 650 watt laser, and that allowed us to increase to 90 micron lasers. And you can see there in one of the graphs that we doubled or tripled the production speed depending on how much frost you're allowing. So our DOE really pushed the boundary of production speed. And then that goes through the Zeiss's AM parameter workflow, which begins with CT scanning these individual coupons that have been printed in different parameter sets, and going through an automated workflow that then segments and evaluates each of those parts, checking for things like where the porosity is distributed. Is it in the fins? Is it in the bulk? And then how much your part deviates from CAD. Our original design and transfer from additive flow software to the printing oversized our parts, so that's something we had to tune back down. You can see there everything is a little bit on the yellow side, and our deviations oversized. And then here we can maybe see clear how we've moved our parameter selection to much faster than what's reported in literature for standard aluminum silicon 10 magnesium, with 350 watt lasers being on that slower side. And then our two improved parameter sets, 1400 millimeters per second, having some porosity, but being mostly dense, and the 2000 millimeters per second being the fastest parameter set we came up with. This then allowed us to input all of this into additive flow software, where we specify that certain channels need to be fully dense surrounding them. And but we still want to maintain thermal compliance. So on the interior and on the touching walls, those need to be of higher density as well. But regions we're going to machine away, that's not as important to be fully dense, or regions that are in the corners that don't transfer much heat, those can be ignored as well. So we got that heat map of where thermal compliance is going on. Then using additive flow, we come up with a couple different solutions, and the GIF there's if once it plays, clicks through how we came up with, or it's video, trade-offs of how much thermal compliance and how much speed of production speed. And then we from this determine where we're wanting to trade off and which values to use based on our performance and of the cost of the part. Then once the part's printed, and then a very tricky part that was able to be solved through the Autodesk workflow that Additive Flow created. We get full laser path control. These zoom ins show that we have our contour pass on the outside, but then on the interior, when it's filling in, it's switching in a single laser pass between 2000 millimeters per second to 1400 millimeters per second in that discrete method. Or a second part was printed with the gradient laser path that stepped down from 2000 to 1400 millimeters per second. And these are chosen to see if there would be a discrete change in porosity or maybe a gap occurring between STLs if you didn't do it in this method. But because we changed the laser speed in the laser path, we're able to seamlessly transfer between a porous region and a fully dense region. Similarly, you could make that two different materials, or you can make it two different microstructures, depending on how you change that. Here are our final reconstruction and comparison to the CAD, where we start with that green model being the original design, the reduced volume, and then the segmented regions of different allocated parameters. Then once our part's printed, it can be aligned to those and compared to the CAD, so you can get the deviation. We're able to fix that deviation and oversizing. We're also to then, because it's an X-ray CT model or a volume here, we can slice through any plane. We begin to slice from that one face to look inside the channels. You can see that the as printed surface looks really rough here. This is a little bit exaggerated because of how X-ray CT picks up the surfaces, but it is also something we can improve in future work. We didn't optimize the surface roughness. We're mainly controlling that higher density in the region around the channels and allowing lower density and faster parameters in non-critical regions. You can also, with X-ray CT, started to even dive into these channels and see that there's a few powder particles stuck on the edges because of the overhangs and things that can't be reached. These can't be sandblasted off. So optimizing for that in the future would be critical. You also see that once we've sliced through, that there is one region of unintended porosity that appeared on the input and output ports. Those were unintended regions, but we're able to detect that with X-ray CT. And because this is a volumetric data set, we can feed this back into Additive Flow, and they can adjust the parameter sets in those regions and fix that in the future. So if there was an issue with changing laser passes in this region, it's unintended, we're able to fix that in future builds. So with this, we were able to come up with new parameter sets for aluminum silicon 10 mag that far exceed standard production processes, and then apply those to the part in a unique way that seamlessly jumps from one speed to higher speed. And Additive Flow then allows you to do all of this by just determining a few boundary conditions, a few regions that need to be maintained, taking in the data from Zeiss's workflow, and then in the end, reducing the QA costs by 75%, because this is a validated process now that we can adjust this and tweak the models and then apply a similar workflow to future parts in the same class.
Thank you. I've also got these, that's actually that part there that was from one of the families, and this was the gradient. Yeah, this is the gradient transition. So you can kind of see that it's a very smooth transition, maybe a bit of exterior gradient. And this is the same part that was X-ray CT walkthrough there that Curtis showed. But we also did this discrete version too, so you can actually visibly see that discrete transition as well. So there we go. So I think, we're nearly at the end now, and then we'll maybe have a few moments of Q&A. But this workflow that we both developed and validated with NPL and Zeiss is reusable. Our software is scalable. We can work with you as an engineering organization or department somewhere, building the relationship. So we can help you either take your existing data, your existing process development, and we can leverage that with a bit of quick calibration. And and we're able to have our software working on your side. So in that case, Curtis is one of our key super users here at ZEISS. But as Tony said, we ran that as a project for our side as well. And then this optimization work will happen. So once you've got that relationship, our technology is scalable across part families, across components. So when a machine and material process material structure relationship is in place, that is scalable across models. And we showed how that predictive accuracy can work across components. And then we have a nice validation step. So we're able then also to take in that ex post facto test data to either re-update models if any tuning and calibration is required, but once you've got this kind of validated prediction, we are seeing quite a lot of conformity between the optimized results and the actual real life components. And I think that's really all we've got time for today. And we've been quite quick. Duan, do we have any time for any questions?
Yeah, for sure. I have some if anyone has any questions, please put them in the Q&A chat. In the meantime, I do have some questions for you guys to get started. And thank you, Alexander, Curtis, and Tony for all that. It was really interesting. My first question is, how do you decide which regions have which parameters, and then how do you define them?
So it's not us deciding as human beings, right? So in this case here, for example, this part here, the channels had a specific parameter that was required to have a specific density to the cooling fluid to go through. But the rest of the space, that's decided by the algorithm based on the objectives that you put in at the beginning. So you can say, do you care about production cost, quality? What are my limits in displacement? What are my limits in thermal behavior? Curtis, do you want to maybe speak a bit about that?
Yeah, it's just like you're saying, you define which regions need to be dense, you define which regions need to be higher thermal compliance or mechanical loading, like in the tensile sample, and then you let the software handle the rest of it.
How do you decide which ones need which, though? You're making a decision.
So the software works like in an iterative optimization process. So if I'm, and we can go into this in a bit of a more detail later, but what happens is, because we've got embedded FEA that's predicting the end part performance, as those material properties are changing in the component based on the laser power, there may be different conductivities there. So our technology then is predicting how that part with that specific volumetric distribution of parameters will perform, and then adjusting the parameters in order to ensure that the right conductivity is in the right place with the thermal application, or the right mechanical properties are realized in the right place based on those upfront objectives. So those boundary conditions that have been placed in at the beginning. And those workflows are repeatable. We can cover that in more detail later.
Yeah. And how sensitive is the process to the geometry? So whether it be a thin wall or a downward facing surface, how do you?
Absolutely sensitive. So it is geometry dependent with parameter dependency. And when I had this, we have this amazing metric here, 2,160 times faster compute. One of those aspects is we've embedded in that process simulation data. So we've worked with the Netfabb process simulation team. We've got a surrogate model, an AI model inside that's simultaneously predicting that residual thermal stress occurring in the process too within the parameters. So the arising material properties due to those thin walls, due to those different geometric features, are accurately accommodated for within our solvers.
Okay, and the final question I'm making out here is, how many parameters do you require to train the AI? Or
how many data points do you mean?
Yeah.
Well, I think Curtis could answer this, because we just had 2 parameters for this 2019 project we did with ZEISS. Was that correct, Curtis?
Yeah, well, 2 parameters used in that, but I don't know if any of that's used to train the AI though. No,
because so to make it clear, the AI training step is to predict the behavior in the printing process. Our decision-making technology is not dependent on a lot of data, because it's the way the algorithm has been built is it's like a digital twin of the process based on physics. And so that's what we can actually still optimize with quite a small set of data. And then as Tony kind of went through with the NPL project that we did, I mean, we didn't have that much data, did we, Tony?
No, it wasn't a huge amount. No, it was mostly the stress strain plots, I think, that you used. So 7 different conditions. You probably just used the average of the 5 tests we did for every condition. So yeah, not that much data really.
Okay, actually, we have one more question from an attendee. Is AF only applicable to metal powder fusion? How about other laser point printing processes like SLA or SLS with polymers?
Thank you, great question. We actually do have a background in the rheology of polymers and polymer additive. We have been focusing on metal additive for the last few years. I mean, our models, of course, would have some equivalency. Of course, you get some plasticity and nonlinearities that can occur within the polymer forming. That's quite interesting to be taken into account. And it is an interesting application, especially within the composites area where you've got anisotropy with similar to the different crystallographic structures that can occur within metal AM. There's some really interesting possibilities there within polymer and polymer composite matrices. And also, we're not just restricted to laser metal powder bed fusion as well. We have and are able to work within DED, WAM, and these other kind of emergent technologies as we come through.
Another question we have is how would this be combined with like CFD simulation? How do those two play together?
So our technology is quite built like a framework, right? So we're able to pull in data from external sources. And so if there's a CFD code or CFD module that could be needed within a system such as this, we're able to have like an API to call in that data, build a model, and have that actually embedded as part of the optimization. In a similar way that we brought in the process simulation, and we've got a really well understood workflow to make that solver that data brought into our technology. So it's a really predefined, easy to deploy.
Great, yeah, because no one piece of software gets used by itself. It's always in combination with others. That's great to see. Okay, I think that's all we have time for. So, Alexander, how can people get in touch with you if they want to learn more about the software?
So welcome to get in touch with our website, additiveflow.com. We've got our team, so you can get through to me directly, alexander@additiveflow.com. We've got Nick at additiveflow.com. And we've really kind of, to make things clear, worked with a lot of different industries from aerospace, oil and gas, and the rest, with cracking problems or end part problems. So there's a lot of specific applications here that we're working with. They can bring in partners too, right? We've got workflows established with NPL, with Zeiss as well, to help support some of this data acquisition step as well.
Great. Okay. Thank you, Alexander. Thank you, Curtis. Thank you, Tony. And thank you, everybody, for tuning in.
Delighted.
If you have any questions reach out directly to Alexander. If you have any questions about 3MEF, check out the 3MEF.io website for all your 3D printing goodness.
Happy Valentine's Day. There we are.
Happy Valentine's Day. There's no romance like process parameters.